enter Frenchman Henri Becquerel. So Becquerel is kind of like, he's kind of like he comes from a line of academic physicists. His grandfather and his father, I think, were both academic physicists. In fact, he inherited his father's chair at some university for engineering and physics. And the point is, right, he's working in a field of study on something else, to do with like photoluminescence, which is just the idea that some things basically seem to glow. They produce some sort of radiation. But X-rays are suddenly like the hot new topic in scientists. So like any good academic, he decides that he basically needs the academic clout. And he decides to basically pivot to working on X-rays and radiation. So his initial hypothesis was that these kinds of like phenomena of radiation, what happens, he theorized that these luminescent materials would absorb radiation energy from the sun and then re-emit that at different rates, which is why they glow for a longer period of time, right? So it's not an unreasonable idea. It turned out to be wrong, but it's not unreasonable. So he's experimenting with uranium salts, and he decides to try and prove his hypothesis, like any good scientist, right? So his experiment that he proposes is basically to have a bunch of uranium salts sit out in the sun, and then basically photograph them. Basically, the process of photography basically imprints the radiation in forms of black marks onto paper at the time. But due to like some really unfortunate coincidences, what happens is at the time Paris is overcast. There's no sun, so he can't really perform his experiment because the salts can't absorb the sun's radiation. But I think what it was is that he had a presentation to the Academy of Sciences very soon after, and he didn't have time to properly do the experiment. So, like someone like last minute preparing an IA perhaps, or last minute preparing a presentation maybe, he decides what to do is he's stored his uranium salts in a drawer this whole time. So there's been no sunlight hitting them. They've had no radiation. He decides to take the photograph. He decides to develop the photographs using those anyway. And what ends up happening is he detects radiation from them. This here, he put like a copper Maltese cross on top of the thing there. So you see it blocks some of the radiation, but not all of it. So what Becquerel's just done is he's proven the existence of spontaneous radioactivity, by which I mean that there's no like other source. So the energy is coming from the material itself. It's not being absorbed from the sun. So after a few more rigorous tests to prove the hypothesis, that's how we arrive at this idea of spontaneous radioactivity. So onto radioactivity proper now. So what is it really? It's the spontaneous, like we said, the idea that it comes from itself. And it's the loss of energy, energy of course being a very important concept all through physics, through radiation. So forms of radiation, what are some forms of radiation we know? Yeah, so alpha and beta are what we call forms of particle radiation. Gamma is a form of electromagnetic radiation. And basically it's energy being transmitted through these forms of radiation. And the other important thing is that they come from what we call unstable nuclei. So what do we mean when we say a nucleus is unstable? Well, okay, so these are graphs basically of different elements on the periodic table with and different isotopes as well. Actually, before that, does everyone understand the concept of what an isotope is?
Yeah.
Okay, so an isotope is, someone say it.
Variation in the number of neutrons in a nucleus.
Yeah. It's the same element. It's the same element. The nucleus has the same number of protons, but there's a different number of neutrons, which changes its mass. So these are different isotopes of different elements, and this is a graph of the number of neutrons they have versus the number of protons. And we see a couple things. So first, just for reference, this is like the straight line where there's the same number of neutrons and protons. There aren't really any elements there except at near the beginning. What we see happening when we kind of graph this out is we get this very rough line in the center. It's called the peninsula of stability. These are the places where isotopes are stable, meaning that they don't decay. And outside of that, on these edges, we see unstable nucleuses that kind of decay. This other graph is more representational of that. It's the line again of stability, and we see we see different particles. These are beta plus emitters and beta minus emitters. We'll explain what that means later when we get to beta decay. But the point here is that this center line is what's stable, and outside of that are unstable isotopes. We'll explain why they're unstable in just a second, but a couple of things to note about this. So stable means that there's no spontaneous radiation from them, and unstable means there is spontaneous radiation. The slope of this line, it starts at about 1, and as you get to larger and larger elements, it gets to about 1.5 very roughly. So for example, lead-246, which is a stable isotope, has roughly 1.51 slope. So yes, but this doesn't really answer the question of why they're unstable, right? Okay, this still doesn't. So this tells us like how we can maybe tell whether an isotope is stable or not, but this doesn't really tell us what makes it stable or not. So what is the and just really quickly, the periodic table of elements here. We see what happens really quickly when we get large is that a lot of them like just tend to be more and more radioactive in the isotopes that are on the periodic table, and the starting from 84, all of them are radioactive, and starting from uranium, which is 92. All of them are not only radioactive, they're so unstable that they can't exist in nature, and they've only been produced in laboratory environments. So what makes these elements unstable? Well, it's the interaction of forces. So if you think about it, right, like a nucleus has what? Neutrons and protons, right? But protons are positively charged, neutrons have no charge. So how does it stay together? Because if the protons are positively charged, then they should be flying apart, shouldn't they? None of the atoms should hold. So what exists is what's called the strong nuclear force, which I think we touched on a little bit last time. The strong nuclear force holds the particles in the nucleus together, and it basically counteracts the electromagnetic force that's trying to push them apart. And what happens when we have too many or too few neutrons is because the strong force also holds neutrons together, we have too much or too little of the interaction of the nuclear force, and it can't hold stable anymore. The nucleus of the atom itself is unstable. And so what decay really is, like what decay is in terms of radiation, especially alpha and beta decay, is an unstable nucleus trying to become stable by changing the number of neutrons or protons it has so that it can be in a stable state. But the nuclear force, it operates between nucleuses and neutrons and protons as well. So what happens is, if the ratio is incorrect, then the strong nuclear force can't hold together against the repulsion of the electromagnetic force. But there's also cases where there are too many neutrons. That's a little more complicated to explain, but it's still the same idea of imbalance of forces.
When the ratio of neutrons to protons is incorrect.
Yeah. So
and they're trying to make up for that.
Basically. So if we return to here, right, the slope is the ratio of neutrons to protons. So if we're off the correct ratio for that particle, again, basically involving very, very specific calculations of the interaction of the strong force and the electromagnetic force. If we're on an incorrect ratio, then what happens is that the particle can't hold together. The electromagnetic force either pushes it away, or the nucleus just can't hold stable. Okay, so we've seen what makes a nucleus unstable. So what can they do to become stable? We have our 3 types of radiation that everyone's maybe heard of, but maybe doesn't quite know in detail yet. We've got alpha, beta, and gamma, and we'll take a look at all 3 of them. So first, we've got alpha radiation. It's a form of particle radiation because what's emitted, they are particles. And where it typically happens is we have large unstable nucleuses turning into smaller, more stable nucleuses. And when that happens, they also emit an alpha particle. So an alpha particle is composed of 2 protons and 2 neutrons. It's the same as helium-4.
Nucleus.
Yeah,
Just the nucleus. Yeah.
the nucleus of helium-4. So we see the idea again of there's an incorrect ratio, so to correct that ratio, we reduce the number of protons and neutrons. This is how we tend to write write out the equations for decay. We have the element here, and what we have is the atomic mass, which is the total number of protons and neutrons, and what we have at the bottom is the number of protons, the proton number or the atomic number. And yeah, and we call we call the initial state the parent, and we call what's produced afterwards the daughter. And then we also have the particles that are emitted. So you see here, we take out 4 in total because we take out 2 protons and 2 neutrons, and specifically we take out 2 protons. So the idea is that by taking those away, we can maybe make the nucleus more stable, and at the same time we emit an alpha particle. So what is the net charge of an alpha particle? Yeah, because there are 2 protons. And what is the atomic mass of an alpha particle? Yeah.
But I have a question.
Yeah.
If you emit the same amount of protons and neutrons, how does that affect the ratio?
The ratio is still affected. If we have
Does
okay, so what is it? Quick. 7 over 8, just as a fraction. You take away 2 from 7, you get 5. You take away 2 from 8, you get 6. 5 over 6 is not the same as 7 over 8.
ratio still changes, but isn't there still an imbalance?
There could be, but the idea is that we want to get to
Minimize the imbalance.
yeah, we want to get to stability, and there are like so it's not like when alpha radiation happens, it isn't like it happens once and that's it. There's multiple. There could be multiple instances of alpha decay. There could be multiple instances of beta decay, and there's also some gamma radiation at the end to take the energy of the nucleus down to what we call its ground state, where it's stable. And there's no like excess energy basically.
It means an atom with a nucleus of polonium-211. That means in total the mass of polonium is 211. And the nucleus has a certain, in red here, total energy that remains constant, and a potential energy that could go above the total energy, therefore giving it enough energy to break away some particles, some chunks of the nucleus, some alpha particles could escape if they gain enough energy. And this is something that happens at random. So radioactivity is a spontaneous and random emission of energy, in the form, in this case, of alpha particles. So I want to reset the nucleus. I am going to observe what happens here, right? Milliseconds. So we have a nucleus of polonium-211. We'll see that when it approaches the half-life, there is a chance of some emission. It could be before, it could be after. This is random, as we said, and this is working as a random simulation. At some point, this nucleus is going to drop an alpha particle away from the nucleus, and that's going to transmute. Oh, there you go. Energy comes away, the alpha particle travels away from the nucleus, and now we have lead-207. So polonium became lead and emitted an alpha particle. And of course, lead is more stable, so here we could wait for the rest of our lives and no emission would come out. So we saw alpha particle, and we saw also some energy coming out of that nucleus. Now let's look at multiple atoms. Let's look at the same phenomena with a lot of atoms. Let's look at atoms of polonium. We know the half-life of polonium, right? And polonium, we saw just now how one single nucleus decays. So here we're looking at, I'm adding a lot of nucleus. Okay. So every now and then you see there's going to be this emission that we saw in one nucleus, but we have multiple atoms. So we have, let's pause it. So we have all the time a percentage of polonium atoms that become lead, right? And as time goes by, we see the yellow polonium atom, the number of polonium atoms decreasing and the number of lead atoms increases. I'm going to reset it. See if I can reset it. No. Let's start again. There we go. So you see how there is a decay, permanent decay happening inside this sample, right? And how here we see the number of lead atoms is increasing as the number of polonium. This is the daughter and this is the father. The yellow is the father. We would see that when it reaches a half-life, we have a chance very close to having 50% of the initial polonium and 50% of the lead. So we're going to pause when we get to the half-life. So that is the definition of half-life. the chance for half the atoms in the sample to decay. You see, this is a simulation that works very well. We reach the half-life. At that moment, 48% and 51%. This is for 100 atoms. I'm using all the atoms in the buckets. Right? So if this continues, we see the nature of this decay, of course, slowing down because there are less polonium and more lead atoms, right? So that is what explains the radioactive decay curve.
So we're going to look at beta radiation next, and this is where it gets a little more complicated. So to start off with, it's also a form of particle radiation, but we have two types of beta decay. We have beta positive and beta negative. So like, what does this really mean? Well, beta positive and beta negative refer to the type of beta particle that's released. A beta negative decay means that an electron is released because the electron is negatively charged, right? What might a beta positive decay emit?
A proton?
Not a proton, because
Electron.
well, not an electron, because an electron would be beta negative, right? And it can't be a proton. Sorry,
Neutron.
a positron, exactly.
What?
I'm not going to give that to you, Yash, because you already knew that.
What's a positron?
So a positron,
Don't worry, he's not giving you some.
yeah, it doesn't even matter today. So a positron, what's a positron? It's a form of antimatter. And antimatter is a strange concept, and we'll yes.
Can I ask a question that nobody's asking? How do they know the nature of the particle that's being emitted? If it's a positive or negative, the mass, the speed, the size, the charge. How do they know about that? We can't see an electron, so what is the way of knowing? You know?
So okay, there's a few different ways of detecting radiation. We'll touch on one of them later, the Geiger-Muller counter. But there's different forms of experimental detection combined with mathematical calculation using the fact that conservation laws exist. So for example, when people suggested it could be a proton earlier, well, we know that doesn't make the reason we know that can't be true is because of the conservation of mass. The same amount of mass needs to be on both sides of the equation to be balanced. So if a proton was emitted, the mass would be imbalanced.
Yeah, but these cyclotrons, I think it is the instrument that they used to see how much they deflect in electric and magnetic fields, right?
Yeah. So there's also the deflection will tell you about the charge, and we'll look
And
at
the mass also, yeah.
and the mass as well because of how much it deflects. So if you guys remember when we looked at fields and we looked at like particles passing through fields, and there in your data booklet there's an equation to calculate like based on the velocity and the mass of that, right? So it's kind of basically they apply the same idea to what's called a cyclotron to detect the charge of the particles. And so to conserve charge, we therefore know it has to be an electron. If a proton turns into a neutron, then well, what's happening to the charge of the atom? This time it's decreasing by 1, so we need to have a positive charge, and that's where we get the positron. Again, we'll talk about what it means to be a positron and then to have antimatter in a second. Yeah.
Sorry, what's the anti-neutrino there? I mean, in your diagram.
Yes, the antineutrino is a very, very interesting question. This is why beta decay is a lot more complicated than alpha decay. There's a couple of things here. We'll touch on we'll get to the neutrino in a second. But before we get there, let's just answer some of these questions. So what is the net charge of beta minus decay?
Yeah, -1.
Yep, and of beta plus decay.
+1.
Okay. And what's the atomic mass?
0.
No, it's not
No,
true.
it's 0.
You can check your data booklets for this one.
Almost.
It's very,
Negligible.
very small. It's the mass of an electron.
Yeah.
1 over
1 over 1,850 roughly.
2,000.
Yeah. Because we're measuring things in terms of the mass of the proton and the neutron, which we say are both roughly 1. They're not quite 1 either. But yeah, the electron's mass compared to them is about 1 over 1,850, which is quite close to 0, but not quite 0. And they're things of even smaller mass, as we will explore later, since we're talking about the neutrino. Okay, so yeah, there's a couple of missing pieces here, right? 1, positrons and antimatter. 2, what's that thing doing down there, the antineutrino? So before we move on to that, are there any questions on this slide?
So,
Yeah.
for excess neutrons to turn into a proton, we need an emit electron.
Yes, to keep the charge balanced. Because when a neutron turns into a proton, the charge of the atom increases by 1, right? So the charge of everything else has to decrease by 1, so we have to have an electron somewhere.
But wouldn't that counter the effect of like oh no, sorry. Never mind.
So if you add one, why don't you need another electron instead to keep it
If you add one, you need
positive
to
and
take away
negative
one.
to be the same?
If you add one, you need to remove one bit of charge. An electron is -1 in terms of charge.
Well, so when you add an electron, then that's when you need the positron.
Well, so the positron is our +1 instead, right? So when you turn a neutron into a proton, when you turn a proton into a neutron, you're taking away the charge by 1, so you need to add one back somewhere. So, well, let's talk about the tail of the neutrino. The tail of the neutrino. Okay. This looks complicated. Well, let's break this down. Okay. Looking at just the first line, what is the situation here? What's going on?
Beta minus.
Beta minus decay, because we're emitting the electron, right? And here we see one of the neutrons turning into a proton, right? Because the proton number increases by 1, but the total number of particles in the nucleus remains the same. A stays the same, Z goes to +1, right? So what is this? That's kind of the $1,000,000 question here. The idea here is that we want to look at energy, right? Because we know energy is conserved, the conservation of energy. This is very, very fundamental in physics. Things have to stay the same. So we basically look at like what the released energy of this decay is by comparing the energies of both sides. So we call this energy Q. It's just a convention. And well, how do we calculate the energies?
MC squared.
Exactly. So we take the mass of this particle times c squared, but then we also have some energy here. So there's still some released energy coming out somewhere, right? For energy to be total. This energy, by the way, it's because in the model, what happens is these particles remain stationary to begin with, right? It's how we treat them in the model. They stay stationary, but beta decay, the electron shoots out. It has some kinetic energy, so that energy has to come from somewhere, and we calculate that kinetic energy by basically subtracting, by taking what energy we have initially and subtracting the energy that at the end that's not accounted for by the kinetic energy. So we just apply. So yeah, so we're gonna have the mass of the X particle times c squared must equal to the mass of X prime, which is the particle after it's undergone beta decay, plus the mass times c squared.
What does C represent in this?
C is the speed of light. We're just applying E equals mc squared here because we're saying that energy has to be conserved, and Einstein tells us that energy is mc squared, right? So, and now this is the mass of an electron times c squared plus well, Q. Q is the released energy. Again, this is in the form of the kinetic energy that the electron has, because it's shooting out, so there has to be energy from somewhere. And by rearranging this and then factoring out the c squared, we arrive at this expression. Now, here's where things get a bit strange. With this expression for energy, well, we can predict what the expected energy of the electron should be, right? Because the particle at the end, it still stays stationary. Yeah. So the energy of the electron at the end, it has to be constant. The kinetic energy of the electron, sorry, it should be constant, right? It should be like on the graph. It should be roughly here. But when we observe, based on the speeds of electrons coming out, what we observe is that it has this weird continuous spectrum of energies. It can have any of these different energies. That makes no sense, right? Something has gone wrong here. And so what happens is by playing around with the mathematical model of all this happening, we eventually come to the conclusion that for conservation of energy, which we all know and love, to stay true, there has to be some other particle here, some tiny particle with almost no mass that we that's so difficult to observe, but it has to be there for energy to stay the same. And that particle is called the neutrino. So the neutrino it's derives from the Italian meaning the small neutral. Yeah, it has a very, very small mass. That's what makes it so difficult to detect. It's, yeah, I think about 50,000 times less than the mass of an electron. There's just one small quibble left, right? The question of, when we looked at this model earlier, we said anti-neutrino, not neutrino. Once again, antimatter comes to haunt us for some reason, right? Why is it an anti-neutrino? Does anyone have like any wild guesses here?
It's electron.
Yeah, so an antineutrino is the antimatter to a neutrino, and we'll talk about what it means for antimatter to be antimatter later. But does anyone have any suggestions for something that we might be missing for why this is an antineutrino? It's the conservation of a different quantum number. So when we do particle physics in 12 point something. There are a lot of different things that are conserved, actually. There's conservation of charge, conservation of mass, conservation of energy that we're all familiar and happy with. But there's these other values. We call them quantum numbers because they exist for different particles. And one of these is called the lepton number. What that means right now isn't important, but the point is it's an antineutrino, again, because we need to obey conservation laws. The reason I'm pointing this out is, instead of just kind of hand-waving it, is like to drive home the point that conservation laws are like the heart of the matter here. It's the idea that things have to stay the same, right? Like unless we introduce some outside element in a closed system, things have to be conserved. So the V is actually the Greek letter nu, which is the symbol we use for the neutrino. And the reason it has a bar over it, that's the symbol for antimatter. And yeah, and it's very specifically the electron neutrino. What happens afterwards is we discover, oh, actually there's like four other neutrinos for other purposes, and they're associated to different matter particles. And yeah, and in this case, this is the electron antineutrino. Yeah.
And so what happens after this reaction? I mean, you're telling me there's this thing, an antineutrino. Where does it go? Does it collide with another neutrino and poof, or
It goes.
what happens?